Today, we're going to embark on a journey into one of the most ambitious and fascinating ideas in modern physics, string theory. By the end of this video, you will be able to explain the core concept of string theory, understand why it's a candidate for a Cantor theory of everything, and describe some of its key mathematical components. At its heart, string theory is an attempt to unify all the fundamental forces of nature into a single, consistent framework. This is a goal that has eluded physicists for decades. The two pillars of modern physics are quantum mechanics, which describes the universe at the smallest scales, and general relativity, which describes gravity and the large-scale structure of the cosmos. Quantum mechanics and general relativity are incredibly successful in their own domains, but they are fundamentally incompatible. When you try to combine them, the mathematics breaks down, leading to infinities that make no physical sense. This is the central problem string theory aims to solve. It offers a radical new perspective on the fundamental building blocks of the universe. So what is this radical new perspective? The core idea of string theory is surprisingly simple. In the standard model of particle physics, the fundamental particles, like electrons and quarks, are treated as point-like objects with no internal structure. This point-like nature is a major source of the problems when trying to combine quantum mechanics and gravity. String theory proposes that these particles are not points at all. Instead, they are tiny, one-dimensional vibrating strings. Imagine a violin string. It can vibrate in many different ways, and each vibration corresponds to a different musical note. In string theory, it's the same principle. Each different vibrational mode of a string corresponds to a different fundamental particle. One vibration might be an electron, another a photon, and another a quark. This is a profound shift. It means that the entire universe, everything we see and interact with, is made up of these tiny, vibrating strings. The properties of the particles we observe are determined by how these strings vibrate. Now, let's look at the two main types of strings that exist in string theory. First, we have open strings. As the name suggests, these strings have two distinct endpoints. The endpoints of an open string are not free to move anywhere. They are constrained to lie on a special type of object called a D-brane. D-branes are extended objects that can have different dimensions. For example, a D1 brane is a line, a D2 brane is a plane, and so on. The endpoints of an open string are stuck on one of these D-branes. The vibrations of open strings are associated with the particles that mediate the fundamental forces of the standard model, like the photon, which carries the electromagnetic force. The second type is closed strings. These strings have no endpoints. They form a closed loop. Closed strings are not confined to D-branes. They can move freely through the entire space-time. The most important particle associated with the vibrations of a closed string is the graviton. The graviton is the hypothetical particle that mediates the force of gravity. This is a crucial point. Because string theory naturally includes a particle that behaves exactly like the graviton, it provides a quantum description of gravity. This is how it solves the problem of unifying gravity with quantum mechanics. To understand the dynamics of these strings, we need to look at the mathematical framework. This is described by an ABA, action principle. An action principle is a fundamental concept in physics. It states that the path a physical system takes is the one that minimizes a quantity called the action. For a point particle, the action is proportional to the length of its path through spacetime. For a string, the action is proportional to the area of the surface it sweeps out as it moves. This surface is called the worldsheet. It's a two-dimensional surface embedded in the higher dimensional spacetime. The first and most intuitive action for a string is the Nambu-Goto action. The Nambu-Gokom action, denoted by S_NG, is simply the area of the worldsheet. Let's break down this equation. The integral is over the worldsheet coordinates, sigma A. The term, T, is the string tension, which is a fundamental constant of the theory. The square root term is the area element. It involves the determinant of the induced metric, H_AB, which measures distances on the worldsheet. So, the Nambu-Goto action is a direct mathematical statement that the string's motion is determined by minimizing the area of its worldsheet. It's the string equivalent of a point particle following the shortest path. While the Nambu-Goto action is geometrically intuitive, it's mathematically difficult to work with, especially when we want to apply the rules of quantum mechanics. This led to the development of the Polyakov action, which is dynamically equivalent to the Nambu-Goto action, but much easier to quantize. Let's look at the terms in this equation. Again, we have the string tension T and the integral over the worldsheet coordinates sigma-a. The key new element is the worldsheet metric, G_ab. This is an auxiliary field, a mathematical tool that we introduced to simplify the problem. It's not a physical metric of spacetime. The term xmu represents the coordinates of the string in the higher dimensional spacetime. The derivatives, partial A xmu, describe how the string's position changes across the worldsheet. The Polyakov action is the starting point for the quantum theory of strings. By applying the rules of quantum mechanics to this action, physicists can derive the properties of the particles that emerge from the string's vibrations. Now, let's address two of the most famous and mind-bending predictions of string theory: extra dimensions and supersymmetry. First, extra dimensions. When you quantize the string, the mathematics is only consistent if spacetime has more than the 4 dimensions we are familiar with. The exact number depends on the specific version of string theory, but it's typically 10 or 11 dimensions. So if there are extra dimensions, why don't we see them? The answer is that they are compactified. Imagine a garden hose. From far away, it looks like a one-dimensional line, but if you get close enough, you see that it has a small, curled-up, circular dimension. Similarly, string theory suggests that the extra dimensions are curled up into tiny, compact spaces, far too small for us to detect with current technology. The shape of these compact spaces determines the properties of the particles we observe. Second, supersymmetry. This is a symmetry that relates two fundamental classes of particles, bosons and fermions. Bosons are force-carrying particles like photons, while fermions are matter particles like electrons. Supersymmetry predicts that for every boson, there is a corresponding fermion partner, and for every fermion, there is a boson partner. These hypothetical particles are called superpartners. Supersymmetry is important for several reasons. It helps to stabilize the theory and solve some technical problems. It also provides a candidate for dark matter, the mysterious substance that makes up most of the mass in the universe. So let's recap what we've learned. We started with the fundamental problem of unifying quantum mechanics and general relativity. String theory offers a solution by proposing that the fundamental building blocks of the universe are not point particles, but tiny vibrating strings. We saw that open strings are confined to d branes and give rise to the particles of the Standard Model, while closed strings can move freely and naturally contain the graviton, the particle of gravity. We explored the mathematical framework, including the Nambu-Goto action, which minimizes the worldsheet area, and the Polyakov action, which is easier to quantize. Finally, we touched upon two of string theory's most intriguing predictions: the existence of extra, compactified dimensions, and supersymmetry, which relates bosons and fermions. It's important to remember that string theory is still a work in progress. It has not yet been experimentally verified, and there are many open questions. However, it remains one of the most promising and beautiful ideas in physics, offering a potential path to a complete and unified understanding of our universe.